morning and welcome to Critical Mineral Exploration, the Next Energy Frontier. Your session chairs are Bill Ambrose and me, Lindsay Ross, and we hope you enjoy participating in this forum, and we encourage attendees, like the presenters, to engage in and express a diverse range of professional views on energy frontiers. Before we start, let me also point out the chat window on the right-hand side of your screen. You can use this space to communicate with speakers and other attendees viewing the presentations. You can also engage with speakers, attendees and exhibitors at any time using the ACE networking portal. We'd like to encourage all attendees to join the post-session Q&A discussion by clicking on the Zoom link provided in the left-hand resources column on the session page. Bill and I have recorded back-to-back introductions for the order of speakers, and I'll introduce the first speaker in Emily Hersh with Critical Minerals for Energy Storage, Lessons from Lithium and Electromobility. Emily's affiliation is as Fellow of the Payne Institute for Public Policy at the Colorado School of Mines. In this presentation, Emily describes the changing nature of the relationship between energy supply and demand and discusses how energy and mineral systems will be coupled into the future. Emily has a Bachelor of Science in Economics from Tulane University and a Master's in International Economic Relations from American University. Emily describes her contribution to policy as one that considers the mineral foundations for the energy transition with an emphasis on battery metals and materials. Welcome, Emily.
Hi, good morning or good afternoon, wherever you are. My name is Emily Sarah Hersh, and I am here to talk to you a little bit today about lithium, and more importantly, the lessons that geology and exploration geology can learn from lithium to consider new opportunities in critical minerals. Before I get started, I just wanted to give the disclaimer that I am not a geologist. I'm an economist who loves rocks. I've been working in the mining industry for 10 years, mostly with exploration projects related to lithium and precious metals in South America. And today I decided to put together a presentation to give a bit of an understanding about what the opportunities are in lithium, some of the nuances that we can learn from the slow growth of the lithium market and the applications that that has for other critical minerals, and more importantly, what the lithium industry especially has to offer for petroleum geologists and the petroleum industry going forward. Welcome to the future, powered by lithium. When I was asked to give this talk, I started doing some more research into the American Association of Petroleum Geologists, and I learned that this organization was actually founded in the early 1900s, around 1917, I believe, in what was known as the golden age of petroleum geology. Now, it was known as the golden age of petroleum geology because it was part of a fundamental and provocative inquiry into basic questions of origin, migration, and entrapment of oil and gas. The characterizations of the origins of this organization and what it meant to the industry at the time really reminds me of what we're going through today in the lithium and in the critical minerals industry, in that we do know a lot about lithium because geology has progressed quite a bit in the last 100 years. But these questions of the origin, migration, entrapment, and then extraction of lithium, where do we find lithium? How did it get there? And what does that mean about how we get it out and use it? Really spoke to me because it's the same ethos and the same energy that attracted me to the lithium industry. If you look around, the future of energy lies in renewable technology that's going to be enabled by critical minerals and not fossil fuels. And I mean this to say that there are things about a cell phone that's run by a battery or a vehicle that's run by a battery that are fundamentally technologically more advanced than trying to run one of these devices directly off of oil and gas. And I am firmly of the belief that we as a society, when it's possible, should be taking steps away from fossil fuels and towards clean energy solutions that don't just allow us to sort of maintain the same quality of life, but help us progress. So I wanted to take a look about what lithium can teach us about how to approach opportunities in critical minerals. I think that we're in a golden age of critical minerals geology. The graphs that you see in front of you are both from a recent publication from the World Bank that talks about the mineral intensity of the clean energy transition. it's sometimes referred to as a dirty truth of the renewable energy industry, but I think it's actually a tremendous opportunity, especially for people like me who love science and love geology, to understand that if we as a society want to move away from fossil fuels and move towards some of these cleaner, more sustainable energy sources, there is a mineral intensity and the growth in demand for certain critical minerals that has never been seen before. The chart here to the left illustrates which applications would use which minerals. You've got wind, solar, concentrated solar, hydro, and energy storage is what I'm going to focus on for batteries. And then which of these minerals have an increased demand. Now, when you look over here to the right, this is the percentage increase. This is the 2050 annual demand that these technologies require as a percentage of 2018 production. So if you take these calculations to be more or less right, which to me they stack up, electrifying transportation will require a 500% increase in the lithium that comes out of the earth and into batteries between now and 2050. And while towards the end of that period, some of that can come from recycling, this means that we need more lithium, and we don't just need it in the ground, we need it out of the ground and into batteries. When we talk about the growth in battery demand, it's important, or in my opinion, makes sense to focus really, especially in the immediate term, on the batteries that are going to go into electric vehicles. This graph comes from Bloomberg, and it shows that the stationary storage and the consumer storage, they are definitely increasing in demand, and by 2030 and onward, you may see that number go up slightly more. But when we're talking about lithium from the standpoint of building mining projects and finding good lithium deposit, it makes sense to say, right, the lithium that we find in the ground someday has to get its way into a car battery, into an electric vehicle battery. Now, it's also important to understand that when we talk about these critical minerals like lithium, it's not an important difference from more traditional commodities, and an important difference from oil and gas is that when you're producing oil, or when you're extracting and refining oil, your final product is that oil. While when you make batteries, the final product, even though it's called a lithium-ion battery, is not just a block of lithium. This is a graphic demonstration, and the numbers are by cost, not by weight, of the different chemicals or the different elements that go into a cathode, which is the positively charged side of a battery, and then what that cathode represents in a battery. So the important takeaways here is that when we're going to find a lithium deposit and figure out how to get that lithium into battery, we need to be thinking from day one, how is this lithium deposit, or how this lithium deposit is hosted, going to impact how the lithium reacts with and how the lithium is able to form part of a battery? But also understand that this isn't such a linear market. You don't see the demand of lithium go up and down exactly with the demand for batteries up and down. It is a nuanced and complex technology, and that means that the extraction step and the advanced processing step need to be taken into consideration from day one. Regardless of the complexities and regardless of how this market is evolving, we can very kind of clearly say that by 2035, even with a conservative estimate for how much lithium demand there will be, we need more lithium. This is unplanned new supply. So even if all of the lithium projects in the world that are planned and discovered went into full production by 2035, we would still have about a 50% shortfall. So the opportunity to go out and not just discover lithium deposits, but characterize and understand how to get that lithium out of the ground and into a battery is of very important demand to the future of transportation. And I want to make the point that lithium production means the production of a stable lithium chemical compound that can be used to produce safe battery materials. What do I mean by that? So in order to kind of understand what I mean by stable lithium chemicals, rather than just lithium, let's take a look at how lithium occurs naturally. Actually, let's not. Let's take a look at why this graph here doesn't get more attention from investment circles. So batteries are fueling exponential growth in the lithium market. And a great way to understand why lithium has people so excited is to understand that the market has more than tripled in dollar terms from 2015 to 2017 and keeps growing bigger and bigger relative to the size it was before. But this dot here in 2015 only represents $1 billion. And that's the first time the entire lithium market was worth $1 billion in the entire history of the lithium industry. Now, to me, $1 billion sounds kind of like a lot of money. I could do a lot with $1 billion. But when you put it into context of other mineral industries, for example, gold, you can kind of see how it's easy to look at this market as small and a bit risky. Let's go to, I guess, a lot of people in this conversation's top favorite topic, petroleum. When you look at the size of the lithium market relative to the oil market, it almost disappears. And I've had real conversations with oil and gas industry leaders who say, why would I look at lithium? The entire market is worth less than the production of one of our wells in Ecuador. To which I say, yes, that's true, but the petroleum industry was able to thrive because people like the founders of this organization saw the opportunity and saw the need to invest in basic understanding of how these environments occurred naturally to get to the growth that we saw today. And I think that lithium is in a similar place and that the skill sets of the petroleum sector have a lot to bring and a lot to add to the industry. So you can see that investment in critical minerals can lag because financial players view these markets as inherently risky. And these critical markets share 4 important attributes that make them very different than oil and gas. One of them is size, which we just talked about. The markets are extremely small in US dollar terms. There's price volatility, which means there are small markets with few players. There's a lack of price transparency because of these small number of players, but also because there's a lot of differences that exist between the lithium chemicals that are bought and sold. And this isn't a commodity, i.e., you don't just go out and purchase some lithium. You don't go out and buy pure lithium. Different battery makers have different chemical compounds that they demand in order to make their production lines get to the final product that their consumers demand. So now we're going to get to the geology bit. So everybody knows that lithium is here on the periodic table. It's the lightest or least dense metal that exists on Earth, which is what makes it both ideal. The density or the energy density of lithium is what makes it an ideal metal for battery. Now, this high density allows for higher performance batteries, but it's also important to understand that it is both extremely energy dense, but lithium as an element is very reactive. So I put this here to demonstrate that the lithium atom is actually unique in that it has the full inner shell, but then only 1 electron in this second shell, meaning that this lithium atom cannot be stable in this form. It has to be combined. It has to give away one of those electrons and exist as a lithium ion. And that means that from an exploration geology standpoint, lithium elementally never occurs freely in nature. It is always part of a chemical compound. So that takes us to, what does a lithium deposit look like? A lithium deposit can look like a lot of things. I think a lot of people are probably familiar with the conventional brine deposits that are in South America. So that's the famous lithium triangle, where these lithium brines are underground and they have to be pumped to the surface and then treated to essentially evaporate the water while using chemistry to drop off contaminants to get to a lithium chemical that's usable in this battery supply chain. There are also new technologies that are being developed, such as direct lithium extraction, to be able to treat some of these conventional brine deposits. Then you've got your hard rock or your spodumene deposits, which are part of lithium-bearing pegmatites. You've got hard rock spodumene deposits all over the world, but they, from an exploration standpoint, are a bit, and I think I'll probably get a lot of people who send comments saying I don't know what I'm talking about here, but these deposits are a lot more difficult to characterize because they are, exploration is needed to explore them pegmatite per pegmatite. It's very difficult to predict how and where the lithium crystals will occur in the next pegmatites in the district. And so this is a very traditional hard rock mining, hard rock exploration type of an operation. Then you've got volcanic tuffs, which are very similar to your clay or sedimentary type deposits, like the lithium deposit that is in Nevada that's being operated by Lithium Americas, as well as an interesting tuff deposit that's in Peru in the Puno region. You've got lithium and lepidolite deposits, and you also have lithium that's being found or lithium that's being worked with in oil field and geothermal brines, like the projects that are in the Smackover Formation in Arkansas, as well as the Salton Sea in Canada. So I think that from this we can take away that lithium is very easy to find, but it's difficult and expensive to commercially extract. Not all lithium deposits are viable projects. So you can see here on this map that there's lithium deposits all over the world. And I have no doubt that the next time that I put this map up, this will be far out of date because there are deposits on every continent, new discoveries are made constantly, but new projects coming out of these discoveries are fewer and further between, partially because we're dealing with new technologies to extract and process lithium, partially because the demand for lithium chemicals is shifting depending on what's going on in the battery industry, and partly because the high risk makes it difficult to get the high levels of capital that are needed to develop new projects. And one of the examples that I like to use is that, yes, technically, a lot of things can be a lithium deposit. The ocean is a lithium-bearing brine, but it's not economic. It would not be economically viable to evaporate the ocean to get to the lithium, but it's a valuable illustration of lithium's relative abundance. So it's important to understand the difference between a lithium raw material, which is what's discovered, and a lithium chemical compound that's ready to go into a battery. The figure to the left kind of takes you through an understanding of how the lithium goes into the electrode, into a cell, and into cell finishing. And it's easy to, I think, comprehend that these are each different and important industrial steps. And the complexity of the relationship from how the lithium gets out of the ground to how it gets into a final battery can help you understand why the lithium market may seem so disjointed sometimes. And it's because the lithium price isn't really an important determinant in the final cost of a battery. And lithium demand is actually driven by how the battery market size is, not the price of lithium. So we can see that it's very possible for battery prices to keep on going down while lithium price goes up, because with economies of scale, increases in efficiency, and technology advances on the battery side, the lithium becomes more in demand regardless of what price level it is. So as batteries become cheaper and more efficient, more batteries are demanded for an increasing number of applications. So to take away an important understanding here is, what do we mean by lithium? The industry talks about the lithium carbonate equivalent when we're trying to compare deposits or estimate a deposit. But the lithium carbonate equivalent, or the contained lithium, is not a good proxy for the final price of the product. So a great example here is, you can see that this is a table for calculating physical contained lithium equivalencies, so the mass balance of lithium. You can say that the same unit of, or 1 gram of lithium carbonate versus 1 gram of lithium hydroxide, that lithium carbonate actually contains more lithium, but lithium hydroxide can be more expensive or a higher cost to the consumer, because when you are doing a battery process, you're going to demand the lithium chemical that you can use in your process, not necessarily the one with more or less lithium in it. So lithium chemical compounds pricing is not based on contained lithium, which is a very interesting departure from how some of the more traditional commodities are priced. A great example that I like to use because it's easy, you can see that the same month, the same product, lithium carbonate of a similar purity level exported from Argentina versus exported from Chile, from somebody who produces technical grade product versus somebody who produces battery grade product, you can see that the average price for the battery grade product was about $12,400 per ton, whereas the same product was $8,200 per ton. This was not because this product contained more lithium. This was not because this was purer lithium. This was because the quality of this chemical was to the standards that can be used into a battery, whereas the quality of this product was to the standards that would have to be reprocessed. And so understanding the complexity and understanding the importance of that advanced chemical processing step is an area where the oil and gas industry and the petroleum exploration industry really has a lot of experience that could be directly brought to bear to improve the lithium industry. The value chain is where it goes from the ground into the battery. And this chemical production step is really where a lot of the value added happens. Now, oil companies are already in a process of transitioning to being energy companies. And I think that as constraints about financing and constraints about carbon footprint and pressure to reduce fossil fuel dependence marches on, that the transition from oil company to energy company will become more pronounced and become a higher priority for these traditional oil and gas players. Oil companies have experience in extraction in challenging conditions. And not only that, oil companies are experienced in advanced upstream chemical processing. The oil and gas refining process is not a one-size-fits-all policy, and oil and gas refining companies have experience making different product mixes depending on different markets. So while the lithium industry is small today, I think that 100 years from now, we will see more and more parallels from the lithium industry early days and the early days of the oil and gas industry. On top of that, oil and gas companies have the balance sheet for lithium. They have the money to do this because these aren't large investments in comparison to what these companies are used to working with. So back to my friend who made the comment about how the entire lithium industry is worth one well in Ecuador. The flip side of that is the entire lithium industry is worth one well in Ecuador. So this is a risk that makes sense for oil and gas companies to take, especially in order to make that transition to becoming energy companies. And finally, lithium is a great place for exploration geologists because there's so much about lithium that we just don't know today. There's so much about the origins of lithium deposits and how different lithium deposits are related to each other, and then understanding how the original deposition of lithium in a deposit can inform us on how to get that lithium out and treat it to go into a battery. So I think that the lithium industry is a very exciting place for young and old, experienced and newer geologists of all ages, genders, shapes, and sizes. And I hope that we can work together to make this the golden age for critical minerals. We're in a period where exploration geology needs a new golden age. And I think that the purpose of the American Association of Petroleum Geologists is very much in line with what's needed to understand and characterize critical minerals from the deposit through the extraction process for this new golden age of critical minerals for the mineral intensity of the transition to clean energy. So I want to thank everybody for your time today. I hope that we get to meet in person next year, and I hope that this presentation was technical enough for those of you who are far above my head geologically, and I am excited to talk through or answer any questions that anybody has after this presentation. Thank you all so much, and have a really good day.
Our second speakers are Mark Jarvis and Lyle Tritton. Their presentation is titled, Nickel is a Critical Mineral for Lithium-Ion Batteries. Mr. Jarvis's career has spanned both mining and oil and gas exploration and development. He is one of the founders of Petroleum, which in 1996 became the first public company to use multiple stage fracking to exploit a tight gas reservoir. He is currently CEO of Giga Metals, developing a world-class nickel cobalt deposit in northern British Columbia in Canada. His co-presenter Lyle Tritton is currently the manager of development for Giga Metals. Mr. Tritton has more than 25 years experience in the nickel industry, including operations, R&D, responsible sourcing, life cycle analysis, and environmental regulatory development. In this presentation, Mark and Lyle provide an overview of the nickel supply chain. They summarize the details of various types of nickel ore bodies, their processing routes, and discuss research of passive sequestration of CO2 in silicate mine residue. This research is important because the ability to measure CO2 uptake in mine residue may make it possible to develop carbon-neutral mines. Please welcome Mark and Lyle.
I'm Mark Jarvis. I'm CEO of GigaMetals, and I will be co-presenting this with Lyle Tritton, who's our Manager of Development. This disclaimer page is required by securities regulators, and I will leave you to read it as a homework assignment. We all know that the electric vehicle revolution is happening. We can see it with our own eyes. The only real argument is about how quickly it's going to happen and what percentage of the fleet will be electric by, say, 2030 or 2040. I say that the rate of expansion of the electric vehicle market will depend on the critical material of nickel for batteries. You can't have the EV revolution without huge new supplies of nickel. Nickel is the part of the lithium-ion battery that stores electrons. It's got excellent electron density. And so if you want your car to go farther on a single charge, you're trying to figure out how to have a higher percentage of nickel in your cathode chemistry. The current market for nickel is approximately 2.3 million tons per year, of which 70% goes to the stainless steel business and roughly 7% to batteries. But batteries are the fastest growing segment of the market. Conservative projections suggest that we'll need 1.18 million tons annually of new nickel supply just for batteries by the year 2040. More aggressive scenarios call for up to about 2 million tons of new Class 1 nickel supply by the year 2030. Even on conservative scenarios, there is a shortage of large nickel projects in the world capable of producing Class 1 nickel economically. Class 1 nickel is nickel that has been purified to 99.8% purity or better. Class 2 nickel, also known as ferronickel, is a mixture of nickel and iron, which is perfectly suitable for the stainless business, but not suitable at all for batteries. Nickel supply is problematic from an ethical sourcing perspective. There's a lot of dirty nickel in the world. An example is the Russians. Nornickel is the cheapest producer of nickel on the planet, but Norilsk is amongst the most polluted areas in the entire world. And then, there are other examples. Does this matter? Well, we think that the electric vehicle revolution, particularly in North America and Europe, is going to cause end users to be looking at their supply chains and caring about where the raw materials come from. We think we've got a shot at being a carbon neutral mine due to the natural carbon sequestration in our tailings. And Lyle will be talking to you more about that. Thank you.
Thank you, Mark. As GigaMetals moves forward to become a responsible metal supplier, we need to think about the two main areas of work underneath the Sustainable Metals banner. The first of these is environmental issues. Carbon footprint is very important as we seek to decarbonize the world, but there are other areas of environmental impact that also require focus, and I'll speak to those a little bit more later in this presentation. We also need to talk about ethical issues, which have come to the forefront both through conflict minerals legislation in the US and Europe, but also over the last few years in some of the growing revelations about the human rights practices in the supply of cobalt from the Democratic Republic of Congo. So here we're thinking about both human rights and health and safety for the workers and the local population, and corruption and similar issues. And then the last part of being a responsible supplier to the industry is being a reliable supplier, ensuring that companies have secure supply chains to meet their strategic goals. And this can be in critical minerals, such as rare earths and nickel and cobalt for batteries, but we've also seen it this year in pandemic issues, the supply of PPE and test materials. So we know we need more nickel, but where are we going to source it from and how? Having spent most of my career as an extractive metallurgist in the nickel business, I could speak for a couple of hours to this, but I won't. What I'd like to point out is really a couple of key features. The nickel business globally is separated into two ore types: laterite ores or oxidic ores that represent about 60 or 70% of the known nickel occurrences in the world, and sulfide ores that represent the balance and which are the dominant form of production historically. Within the laterite business, there's two treatment methodologies used. Higher grade ores are typically treated by thermal drying and reduction and electric smelting at a high carbon footprint to produce an iron nickel alloy, nickel pig iron or ferronickel, class 2 nickel that's good for stainless steel production, not good for batteries. Lower grade ores are typically chemically treated. The entire ore body is leached with sulfuric acid under high temperatures. The undesirable elements are precipitated, go to the tailings facility, and the desirable elements are recovered into an intermediate for further purification. This has an intermediate carbon footprint. Sulfide ores have an advantage in that the ore itself is amenable to beneficiation. Using a technology called froth flotation, the ore can be upgraded to an intermediate concentrate that can then be shipped globally for further treatment. Typically, this is smelting and refining. However, high-grade concentrates can also be directly leached and purified to recover class 1 nickel. So we have two main ways of getting class 1 nickel, from low-grade laterite ores or from sulfide ores, and then we have a way of creating class 2 nickel. So the production of class 1 nickel from laterite ores typically involves mining thin tropical deposits. This creates a very large environmental footprint because these deposits are typically 2 to 20 meters thick, so the mine site is very large, and you also have a large tailings facility in a biosensitive area. Further, because this ore must be processed chemically, you're creating a tailings material that is chemical precipitates rather than unaltered host rock materials. And the extreme conditions at which these projects operate has led to some very troubled project histories. Shown here are the startup curves for all of the high-pressure acid leach projects started since 1998. And what you'll notice is that it takes a long time to ramp these projects up to any kind of steady-state production. In fact, the three best projects, shown by the green check line, took on average 5 years to even approach 100% operating rate. Production of class 1 nickel from sulfide mines in the conventional sense has used underground mining techniques to mine higher grade ores that are relatively complex in terms of the payable metals. They contain nickel, copper, cobalt, platinum group metals, PGMs, as well as precious metals. This results in a moderately complex beneficiation circuit to separate these into various concentrates that can then be shipped globally for smelting. But the environmental footprint is relatively low because of the underground mining. When high-grade concentrates are produced, these can sometimes be directly leached to produce class 1 nickel without going through the smelting step. With Turnagain, we're looking at a relatively new class of nickel sulfide projects, the ultramafic nickel projects. These are peridotite and pyroxenite rocks featuring minerals such as olivine, and typically feature lower equivalent grades. The nickel is typically in solid solution within the magnesium silicate host rocks, which is generally unrecoverable. However, where you have an ultramafic deposit that has been in contact with sulfur during the melt phase, the nickel is extracted out of the host rocks into a nickel sulfide mineral that can then be recovered. Typically, these are large, thick surface deposits, and the alteration of the minerals with weathering from olivine to, say, serpentine gives a varying complexity of processing. One of the interesting features of working with ultramafic rocks is that they naturally go through a process of mineral carbonation. Minerals such as olivine, shown here, naturally react with CO2 in a slow and complex process over geologic time periods, but can react with a substantial amount of CO2 in due course. Full carbonation of olivine or serpentine can hold up to 1/2 ton of CO2 per ton of original mineral. The key is to enhance the natural rate into something more interesting to industrial processing, and this can be done through a number of means: grinding the ore finer, thermally pre-treating the ore, using high purity CO2, operating at high temperatures and pressures, or using chemical modifiers can all enhance the natural rate of carbonation. What we know for sure is that the volume of ultramafic rocks in the world make this one of the greatest opportunities for decarbonizing the world from a removal standpoint. We know that passive carbonation in mine tailings exists today. It's been documented at a number of mines around the world, including these 3 displayed here, which were documented by Dr. Greg Dipple of the University of British Columbia and his colleagues. 2 of these are mines in northern Canada. One is a nickel mine in Western Australia, demonstrating that the CO2 sequestration happened under a range of climatic and mineralogical conditions. For reference, Turnagain ores are about 39% magnesium oxide content, and this is an important parameter for the carbonation. As we go forward, Giga is supporting research into the distribution of reactive minerals within the ore, the capacity of the ore or tailings to carbonate, and how we might enhance the passive carbonation. One of the interesting aspects of mineral carbonation is that it increases the material strength of the tailings deposit, which reduces tailings storage risks in 2 important ways. One is by reducing the amount of dust generated from a tailings facility because the surface grains are more locked together. But more importantly, the locking together of grains throughout the deposit increases the overall strength, as shown here, which reduces the propensity to flow in the event of a tailings dam failure, such as we've seen in Brazil in the last couple of years. So, for the geologists out there, let's look at the mineralogy of the Turnagain deposit. What we have here are 3 composites created from a variety of variability samples representing different lithologies across the deposit. And what we see is a small but varying range of sulfide components. This is the nickel extracted into a recoverable sulfide, with a very large component of serpentine and olivine in the green and purple, which make up the majority of the host rock, which is that which is susceptible to carbonation. Our plan at Turnagain is to optimize the project to be that responsible supplier of nickel. We want to avoid CO2 generation within the facility. We'll have access to clean hydroelectric power from the British Columbia grid, which is great, but we also plan to look at things like the mine haul fleet and aim towards battery or hydrogen fuel cell electric vehicles to further reduce that CO2 generation footprint of the site. We intend to optimize the flow sheet for metallurgy. First and foremost, we're a nickel producer, and then we'll consider the carbonation in the tailings storage facility. We'll look at the tailings deposition methodology. We'll manage the surface area of the tailings facility so that we'll have subaerial deposition. Most of the tailings exposed to air, which will increase the reaction rate with CO2. Only a small pond for process plant water. And we'll use geometallurgy to focus our efforts on the most reactive minerals and make sure that we give them the best chance at carbonation. Overall, this should drive our CO2 footprint down and our profits up. When we talk about optimizing the flow sheet for metallurgy at Turnagain, this is in order to ensure that we are a reliable supplier of nickel. We're planning a simple flow sheet with proven operations, crushing and grinding of the run-of-mine ore, a single flotation circuit to produce the high-grade nickel concentrate, about 1% of the overall ore mass, with 99% of that ore mass going into a responsibly managed tailings facility where we ensure that we minimize the risks to people and environment while enhancing the availability for carbonation. The maintenance of this equipment is relatively straightforward. No high pressures, high temperatures, exotic materials, or significantly hazardous chemicals. And the required labor skills are available within British Columbia. The map you see here is all of the operating mines within British Columbia, many of which are metal mines operating circuits exactly like what we offer here at Turnagain. Giga Metals' plan to become a responsible and reliable supplier of nickel to the electric vehicle industry starts with our excellent mining-friendly jurisdiction. British Columbia and Canada are world leaders in the environmental regulatory oversight and environmental permitting, which includes not just the environmental impacts, but also social impacts. British Columbia has recently adopted the UN Declaration on the Rights of Indigenous People into legislation, putting legal force behind what has historically been good practice. We have good relations with our local Indigenous groups and communities who are supportive of the mining industry and indeed have a mining history themselves going back millennia. We're planning a project with a low overall environmental footprint, relatively constrained mining area, tailings deposition of unaltered host rock materials, and no use of significantly hazardous chemicals. We're planning for low carbon nickel production through the use of hydroelectric power, through a focus on reducing greenhouse gas generation within the operating area of the mine, and through enhancing the natural mineral carbonation of our tailings material. Research and engineering into all of these aspects continues, and we hope to be updating you later on our progress towards becoming a leading supplier of nickel to electric vehicle batteries. On behalf of Giga Metals, Mark Jarvis and I would like to thank you for your attention. We have a few minutes left to answer questions within this forum, and follow-up questions can always be directed to us at the contact details provided here. Thank you very much.
I'll now introduce our third speaker, Michael Campbell, with sources of rare earth elements in the US and the world. Michael's affiliations with I2M Consulting, where he's a senior principal and chief geologist and chief hydrogeologist. Michael and his co-authors in this presentation discuss where and how rare earth elements occur with uranium and thorium mineralization, how much is available on Earth, and in what forms do rare earth elements occur. Michael addresses the question as to whether there exists sufficient rare earth elements to meet industrial demands. Michael D. Campbell is a graduate of The Ohio State University with a bachelor's degree in geology and hydrogeology, and has a master's degree in geology and geophysics from Rice University. To date, Michael has been serving as a professional geologist and hydrogeologist for 54 years, is a member of the AAPG since 1974, and Michael is a founding member of the Energy Minerals Division in 1977. In 2010, he was elected as president of the EMD. Michael is chair of the EMD's Uranium Committee. Welcome, Michael.
My name is Michael D. Campbell. I am chairman of the Uranium Committee of the Energy Minerals Division, and we have put together this presentation concerning the sources of rare earth elements in the United States and in the world. I'm joined today in putting together this presentation, Bob Gregory, who is vice chair of government for the UCOM Uranium Committee. He's from the Wyoming State Geological Survey. I'm also joined by Stephen Sabray, who is, serves as vice chair of academia. He's from the University of Nebraska. Also, James Conca, who is a well-known energy expert in the world. He also provides a lot of input over the years, and he's a member of our advisory group. Now, let me explain, since we have limited amount of time, this presentation was put together for long-term use, in that we have added a lot of references, links to papers that we'll be discussing, only summary. So let me lay the foundation in that way. We also bring your attention that members of the Uranium Committee also presented another paper by Stephen Sabray in theme 9, and we suggest that you may want to look at that as well. We've provided a link there on this this presentation should you want to download it and convert it to a PDF. At this stage, let me explain that we're going to be going rather quickly, and we may run out of space and time. So let me begin now. The rare earth fields are quite large now. There's a lot of work going on all over the world. And when we put together our initial assessment of rare earth activities for this conference, we realized there's going to be a lot to cover. So we've prepared two versions of of our presentation. One is a large, rather large, what is it, a 65-minute video that covers all the areas we felt we needed to cover. And then a 20-minute sort of summary version. The summary of development. The rares have been mined since 1900s. And as you can see, in about 1960, 1950, we started finding uses. You can see in 1952 is when Mountain Pass in California started mining. And then you can see this is certainly not linear, but this curve on world production and demand is going up rather quickly, and with all the changes in the demand depending on the world and local financial conditions. The technology has been driven by geoscience research. It's been driven by geoscience discovery and more research. And then comes the industrial applications, engineering applications. That's clear. This is a geologically driven process of exploration, and which is true for all natural resources. Industrial development, of course, depends on the exploration, but also on the grade tonnage evaluations to how far it gets along, whether product demand or resource price or economic pressure, or even geopolitical interaction comes into play. That means with all this activity, there's a fair amount of jobs at stake here, and we've included a list for jobs links in Australia, the UK, and the US here for your particular benefit in case you should need something like that. Let's get into the really interesting things worldwide and in the US. As you probably have heard, there's a place called Mountain Pass that is a major carbonatite, and that definition is included here for you if you want to click on some of the references. And I won't have time to go into too much detail, but Mountain Pass used to be our major producer of rare earths for many years until the economics and the environmental issues got a little troublesome, and they had to slow down. And about that time is when China got into the mix and started controlling all the distribution, or most of the distribution. But let's look at this map first. Here's China, and I got to say, China's got huge amounts of high quality, high grade rare earths, and not just one, not in the just Inner Mongolia right here, but they have other major deposits, and some of them are carbonatites, and others are alkaline igneous related to intrusions. So you can see here they are here, but here's Mountain Pass. But at the same time, here's the new Texas project. Here's the Eastern Seward Peninsula project that we've been working on. You'll see the coal carbonatite here is discussed right over on this side with a good link that will give you an idea of what's going on. This is not developed yet, but as you'll see in a later slide, Russia has a fair amount of rare earths as well, and we'll see how that goes. And as you can also see, various deposits, both carbonatite and peralkaline igneous intrusive types of occurrences are not uncommon in the world and increasing rather rapidly as exploration expands. Excuse me, but the heavy minerals are also have plenty of monazite and other rare earth containing sands. And there's a few deposits that are residual clays that have retained the rare earth and it didn't wash away, let's say. And of course, the phosphates in the world, not only in Morocco, but in Queensland and Northern Territory, where I worked on in the early 60s, that I noticed had a fair amount of rare earths in it. And because these are bulk mines, that means huge tonnage, there's a huge amount of secondary available rare earths in these kind of deposits. Okay, let's move on to the next, about 55 known rare earth occurrences, and the numbers are increasing, as I said, and those are coming in Canada, more in Australia, and of course I'll bet China is still looking other areas, mostly looking for shallower, less expensive to mine kind of projects. There are so many, in fact, that as I say here in the bottom right, and to remind me to share with you that there are so many of these particular deposits that many of them will just end up as sites for geologist field trips in the future decades ahead of us. In this slide, shows some models of rare earth occurrence in the world in a broad geological framework, all the way from calc-alkaline magnetism and to cratonic involvement in back arc areas. You can get an idea of how widespread these rare earth deposits, or at least mineralization, are by just this figure in type A. More specifically, you can see in this graphic on the right here, where you see a big trachyte or cyanite intrusion from a base carbonatite or a cyanite mass that ends up in coming out and through various sedimentary areas into at or near the surface. And this is a good example here that shows the rare earth veins, mostly with fluoride involvement and uranium and thorium in many veins. It's typical of the one of the occurrence we worked on in the Seward Peninsula in Alaska. Down here at the bottom, you can see the seafloor graphic showing the accumulations and nodules and what have you that's gaining a lot of attention. But my son, who is heavily involved in marine activities, in fact, he founded the marinebio.org, and he's not too keen on such mining because he says that, and it's understandable, that it disturbs the surface, and so a lot of the critters living down there may have a little trouble. But the fact is, we'll see how that goes. This particular slide on the right here is a good example of how volcanism containing rare earths contribute to not only the seafloor but also coal over here on the right hand side, and that's covered in the larger production that we've put out in the video. Okay, let's go on to the next slide. The mother lode, if you will, of rare earths right now. This is the Benyon-Obo rare earth mine complex. There's more than one mine here. You can see a pit here, and a pit here. These are all waste piles, tailings piles. Those are the ones that mostly get the and down in here, and here's some more waste piles. Those are the ones that usually get most of the PR. And for example, in 60 Minutes, if you happen to see that one that piece that they had a few months ago, that was, they emphasized, oh, look at the waste piles, and isn't that terrible? And yes, there's environmental issues, but the Chinese get after these things, and you can see there's a town built right on top of the mine to provide the help and assistance. And I understand that the Chinese are beginning to add new environmental controls and improve conditions. So they know what they need to do, and it's just a matter of with the world, with their eyes on, with the world's eye on what's going on, they'll respond. So these mined ores and process oxides are being developed, but China is also realizing that not only do they need to just produce the rare earth, but they also have to, if they want to keep control of much of the market, keep control of the produced metals and the alloys that are being used, and the end products such as magnets that goes into electric cars and rail lines. And at the other end, they have figured out that not only do they mine, but they also have to sort of control other sources. So we know for a fact that they're out talking to a number of people, mining companies in Australia, for example, and South Africa and elsewhere for acquisition of those projects. And of course, they would put them, they wouldn't develop them, or they would develop them very slowly to protect their production, not unlike De Beers does in the diamond business. So this is nothing new. This is just pure capitalism, and we have to compete accordingly. Look at the new rare earth, let's call them, in the one in Texas that will likely be on in production pretty soon. Because not only do you have to mine it, if you really want to get into the rare earth business, you also have to process it into oxides before it has any major price to it. And that's what the USA Rare Earth Company, which has sort of taken a lead in the projects in Texas. The Texas Mineral Resource Corp did the development, early development, although it was also, this deposit was also known for some time, but they didn't know how useful it might be. And by useful, I mean, it not only has rare earths, and you can see here's some of the sawtooth, but if you notice, it's heavily enriched, excuse me, heavily enriched in heavy rare earths, which is, some of these products are extremely high priced. So, but it's not only that, it's also because the deposit has hafnium and beryllium and gallium and zircon in what appears to be economic concentrations. But at the same time, there's a sulfate byproduct that is being considered to come out of this thing, and that's going to be producing sodium, potassium, manganese, magnesium, iron, and even some aluminum. Excuse me. The other thing about this Round Top deposit is that it's near rail facilities, just a few miles away. I remember I passed it, the site on I-10 going west many times, and there's a rail line, east-west rail line that comes across over there that they'll be able to provide. It provides market access to them for their bulk product distribution. The mineralization there around top is, excuse me, is in rhyolite as opposed to igneous and metamorphic intrusive igneous, not intrusive igneous. This is intrusive, but it's a rhyolite, very different kind of thing, and some odd minerals. But the basanite here is your common rare earth containing mineral that is mostly produced in the California deposit as well. But there's other elements that contain, and each one of these minerals have to be, let's say, broken up, and the rares have to be released in a special way. That's why Round Top is coming on rather strongly, because they've made a deal to develop a reprocessing plant and refining plant in Denver that's underway right now. And if they can get that underway and get their products ready, they could be in operation in the next year or so. Most of the other projects are looking at lead times of 5, 6, 7, 8 years out, which, there may be some merit to that. But this is a particularly interesting because it's a heap leach project. In other words, they mine it, and then put it in a big pile. And with various fluids, they can remove a lot of the rare earths. And also some yttrium and scandium comes out, come to think of it, of this heap leach project. So we'll talk a little bit about a basket product, meaning rare earths has this unusual capability of having many products, and each one has different prices associated. Sometimes you can get a very large amount of money for one element and not so much on another element. When you put them all together, makes exploration and development interesting. On whole, Texas is under development for these particular kinds of projects. So I expect more is going to be showing up. Of course, they have to end up with special relations in terms of what's present and what's marketable. So this slide shows one of the major rare earth deposits, and this time in Alaska. Although we cover the other states that have rare earths in the large comprehensive form of our presentation. But the Buchan Mountain here has been known for some time, and it's got reserve bases already, a resource base already calculated, and it's more or less ready for operation because it's got all the necessary aspects. There's the ease of operation for shipping products out, and that means a lot of the time that means a lower cost to operate. There's another deposit that we worked on that was been known for some time, that the NURI program in the early 1970s, that we did some work on some of the results of that program, and we found a rather interesting rare earth and uranium and thorium too. So I won't go into any detail there except to refer you to the paper that we did. We also found that in that area, there's also an interesting basin that is circular in nature that we'd like to talk about until we get back up there and do some drilling. It looks like an impact crater to us, about 35 miles across. And as soon as we get back up there and do some drilling at the interface below the tertiary basin sediments in its contact with the underlying igneous and metamorphic rocks, we should be able to tell based on, of course, the silica nanoparticles and the iridium and other features that are usually present at that interface. So let's, and that basin is also important because we think this rare earth, or these uranium deposits here, have contributed to the basin to create a new uranium rollfront district. Yeah, this slide shows the world production for rare earths for, I think it's 2018, at a level of about 170,000 metric tons. That has increased to 210,000 metric tons of rare earth oxides, and it's expected to increase even more in 2020 unless the pandemic has interrupted that particular flow. China has been controlling about 70% of the market. There's a lot of illegal escape of rare earths out China borders that they've been trying to eliminate, probably through Vietnam and other border areas. But it also shows here the Mountain Pass production that they started up again in 2018 or 2019, and increased to 26,000 tons of rare earth oxide. So how long they stay in business is another matter. You can see on the graph on the left here that Australia's got a pretty substantial part of the market at what was it, 20,000 tons last year, or in 2018, and that's probably staying about the same. We've put together this table that shows prices and use of the rare earths. As you can see, the principal uses there of the various metal oxides, the prices of 2008 and the prices of 2019. We updated everything to 2020. As you can see, there's major fluctuations in price, which makes it very difficult to do economic evaluations, such as this kind of projects we do for our mining clients, mostly in Australia, on projects all over the world. But the fact is, that's the problem with rare earth in their development because of the rapid fluctuation of prices. I put all the deposits in perspective here, and even in Namibia, a major rare earth, but it primarily is producing yttrium, which sort of separates it from the others. Here you see it here on the top of the market basket, meaning it has yttrium, but also a lot of other things that you get good money for in the market. And here's the the main Chinese and deposit, and there's the round top. So anyway, I've summarized what the limitations of the rare earth basket price approach is, as opposed to just operation and maintenance costs, so and capital costs. So have a read of that, and I think you'll find it of interest if you're gonna. If you want to know more details about the actual economics of, let me say that there's a price demand complexity to this, where you saw the neodymium dysprosium peak, that as mine products were developed, the price went down, but with increasing demand of 3 to 7% CAGR, which is the compound annual growth rate calculations, it's still going up. So we're in an interesting situation, and with respect to reserve base, there's a possibility that down here at the bottom you see that I mentioned something about the development of off-world resources. If in fact some of those asteroids are just loaded with rare earths, where we can get huge quantities of very high grade, all of a sudden all of the rare earth deposits on Earth may become uneconomic. Yes, it's going to cost a lot to get up there, but maybe the unit price of these rare earths will come down as we develop the technology. Yes, this was an abbreviated version of our full presentation, so I would encourage you to either take a look at the PDF version, which you won't get any narration, but you'll have all the links and the graphics that are associated with our presentation. But the fact remains is the larger video will cover everything we wanted to cover. So I appreciate your attention, and thank you very much. In case you have any questions, feel free to call me at i2mconsulting.com. That you'll see a number for telephones in there if you like, or send me an email. I'd be glad to talk to you and about projects or employment or what have you. So feel free. Thank you very much.
Our fourth presentation is by Lindsay Ross and David Beckett to present critical minerals, the Petroleum Geoscientist, and the wider application of hydrocarbon exploration and development techniques and business practices. Lindsay is the director and exploration geologist with Cherryvale Partners. He graduated from the University of Southern Queensland with an applied science degree in geology, and has spent 10 years working in minerals exploration and development across Australia and West Africa, and a further 20 years in oil and gas exploration and new ventures onshore and offshore Australia, Papua New Guinea, Indonesia, and New Zealand. Lindsay is currently co-chair of the AAPG's Critical Minerals Committee and is working on methods for applying petroleum exploration technology to critical minerals. His co-presenter, David Beckett, is the director of Rockley Advisory. David graduated from Exeter University with a BSc honors in geology, and subsequently from the University of Reading with a PhD in sedimentology. He has spent 30 years working in oil and gas exploration and production across the Americas, the United Kingdom and Europe, North Africa, the Middle East, Southeast Asia, and Asia Pacific region in both technical and senior leadership roles. Lindsay and David's presentation is about demonstrating a blueprint for an energy company that could be both sustainable and independent of government financial assistance to make it work on Earth and then take the model to the moon. Please welcome Lindsay and Dave.
Good morning. My name is Lindsay Ross, and I'll take us through the first 8 slides of the presentation before handing over to my co-author David Beckett at slide 9. The purpose of the presentation is to outline a case for how the oil and gas business, and the mining business for that matter, could respond to the new energy economy. The concept is based upon leveraging competitive advantage of the geosciences and engineering wherever possible, but for this presentation, the case is outlined for moving into enhanced geothermal systems and ultimately minerals production by a method of continuous hydraulic production. The distinction between a critical mineral, as defined on this slide, and a strategic mineral is based on the direct military application for strategic minerals, but a broader industrial application for critical minerals. A strategic mineral is a critical mineral, but a critical mineral is not necessarily a strategic mineral. Different countries or industries may define criticality according to their specific circumstances. As far as critical minerals or critical energy minerals for battery storage are concerned, this is an interesting and especially important space to watch as rapid developments are occurring and have significant disruptive potential. Consider, for instance, the implications of a rechargeable battery with the energy density of petroleum. How far away is that from a commercial reality? In terms of CO2 emissions, the graph on the left-hand side demonstrates the forecast 2050 cumulative mass of CO2 produced through extraction and processing for a selection of critical minerals and is allocated by colour to solar PV in yellow and, for example, battery energy storage in light green. The graph on the right-hand side demonstrates demand for a broad list of commodities in terms of the annual demand increase in 2050 as a percentage of 2018 production and the annual forecast demand in millions of tonnes at 2050. The extraction and processing of most of these minerals is the exclusive domain of the conventional mining or hard rock business. But will this remain the case for all minerals? Is there a disruption coming to the conventional mining model? We think so for some minerals, and we consider it likely to be application of hydraulic fracturing and extraction by a form of continuous hydraulic production, where we can envision an industry vastly different to what we see today. On the left-hand side, we've represented the traditional oil and gas company as vertically integrated from E&P to gas-fired electricity generation and petroleum refining. On the right-hand side, we have a similar schematic for the traditional mining company. Efforts by both the oil and gas industry and miners to participate in the new energy or renewable energy economy are represented by a green square with icons for solar, wind and bio at the left for oil and gas and right for miners. This, along with carbon sequestration, appears to be the pathway some of the larger oil and gas companies are moving along, some with pace. Yet another pathway is worthy of consideration, and it's one by which technical competitive advantage is leveraged. The application to the enhanced geothermal systems of unconventional oilfield tech from hard-won hydraulic expertise is currently underway. But in our thinking, enhanced geothermal systems is not an end in itself, but a step towards realising a further advance in the form of hydraulic extraction of minerals, critical or otherwise. Interestingly, by moving into the enhanced geothermal systems space, the oil and gas industry and the mining industry can each leverage technical competencies and become integrated future energy resource industries, and along the way, travel through the commercialisation pathway in electricity generation via EGS. We make the distinction between this future pathway and the current investment in solar, wind and other renewables, not as an either-or proposition, but one that provides maximum leverage on technical competitive advantages. I'll come back to this later, but what advantage does an oil company have in solar farms or wind turbines versus the existing market participants? That said, by the same logic, what technical competitive advantage does an oil and gas geoscientist have in the conventional hard rock geoscientific space? Well, arguably more than is credited, as we tend to overlook it, and because of increasing specialisation over time, we have a tendency to stay in our lanes or silos or technical niches, not all of us, but many. On this slide, we've split commodity exploration schemes into minerals exploration on the left-hand side and oil and gas on the right-hand side. On the far left-hand side, we have an image from Geoscience Australia, where we recognise the traditional minerals exploration systems concepts, for example, a hydrothermal system as one of source, migration, trap, and above that figure, a hierarchy of maps from models integrated into what resembles a plane map in a play-based exploration context. On the far right-hand side, we present conceptually the play-based exploration schema familiar to most of us. In the center of the slide, we're depicting a direct comparison of minerals exploration hierarchies and scalars, and on the right face of the pyramid, the hierarchies for oil and gas, with the faces coalescing at the top, beyond the prospect at the portfolio. In the portfolio space, we use commercial metrics and in turn communicate value, risk and reward with our non-geoscience colleagues. From tectonics at the basin rising through the comparisons of province to basin, system to play, and at each level, we consider the correlative techniques and analyses in oil and gas versus minerals exploration. To expedite the case being presented, we'll drill in straight away and have a look at mineral systems exploration using a well understood oil and gas tool in the form of the Petroleum Systems event chart. At the top of the slide, we're moving from the left with the conventional chart through the center with the unconventional chart and to the right hand side in a chart that we've applied to a hydrothermal mineral system. So we have a minerals exploration scheme represented in the Petroleum Systems event chart. In the lower half of the slide, we characterize the geoscientific disciplines in a concave to the right shape distribution of competencies surrounding a circle containing the interpretation and processing systems that are used for analysis. So for example, fluid rock interaction in oil and gas, that's diagenesis, and in minerals, that's alteration mapping, broadly. Other comparisons are in the slide, including how we describe the spatial distribution of the commodity or commodities under review. Basically, these are all just learned methods of analysis, and the distinction between hard rock and soft rock starts to fade into a non-useful distinction. Disruption and the progress we can make from it has a habit of allowing us to see some barriers rendered obsolete, and we can develop new ways and new approaches in that light. To this end, importing and developing new geoscientific capabilities into this scheme will require the adoption of some geoscience staff, not usually considered at home in an oil and gas company, likewise for a mining house. Cross-skilling and new team structures are required to action this approach. Dave will come to this later in the presentation. This graph demonstrates historical oil and gas production for the US as a blue solid line for conventional and a solid orange line for unconventional oil and gas, based on data from the EIA. Unconventional forecast production is shown as the orange dashed line and is based purely on my speculation, as the coloured smaller dashed lines forward to 2020, which represent different commodities that may be produced through continuous hydraulic production. The main point of this slide is to communicate that a window exists for us to develop enhanced geothermal systems, after which we may see unconventional production of minerals, which would be similar in its disruptive scale, if not greater than what we experience with unconventional hydrocarbons in the US. The production of minerals through this approach has obvious environmental and social benefits, but it would also open up commercialization pathways, for example, stranded near mine deposits, which are currently uneconomic by conventional mining, open cut or underground. In this slide, we have a schematic stylizing what hydraulic production could look like at mine scale, with splays of producers and injectors connecting the deposit to surface production and processing facilities. On the left-hand side is a series of points suggesting some challenges to overcome, things that we can identify, such as the ore body imaging, grade distribution, and how you'd handle development drilling. Ore body zonal isolations, cementing and completions, and the chemo-mechanical ore body degradation and fracture maintenance. Not insubstantial challenges, but who else is better placed to solve these challenges than the people that came up with hydraulic fracturing? We have the technological capability to meet them, and I'll pose the question again. What advantage do oil and gas companies have in solar PV, wind, tide, or hydrogen versus the current players, if you move into that market? I'll hand over to Dave at this point before returning later to discuss some play-based exploration concepts as they relate to critical minerals.
Thanks, Lindsay, and good morning. I'm Dave Beckett. In the preceding slides of the presentation, Lindsay's covered critical mineral synergies and exploration concepts. Over the next few slides, I'm going to briefly touch on what oil and gas companies might look like in the future and consider some of the factors that might drive their success. So, why does the world still need an oil and gas industry? Well, the main reason for that is, as most forecasts indicate, for at least the next several decades, the demand for oil and gas will likely exceed production, and by a larger margin for gas than for oil. And these predictions too may be conservative, as they don't fully factor in current exploration shortfalls. As well, some of the fuel types that drive essential global transport systems, like aviation and marine bunker fuels, are hard to replace. Other derivatives essential to the global economy, such as fertilizers and plastic, are also likely to see strong demand growth over the coming decades. These byproducts of oil and gas exploration will only become more costly as the oil and gas industry declines, and that will potentially have an adverse effect on the global economy. The effective transition to renewable energy systems is going to rely on a strong global economy to drive it. So it follows that an untimely decline in the oil and gas industry will likely impede rather than assist that transition. So, if we accept that there's a future for oil and gas companies, how can they best adapt to the changing nature of the global energy market and to public perception? While it's understandable that companies will seek to reflect public values, the industry really has little to be ashamed of over its role in providing the raw materials of energy that power global society and commerce, and for its contribution over the years in lifting the developing world out of poverty. The industry might benefit from getting back on the front foot through advocacy and education and using that to stake its essential place in the energy transition. Our industry should embrace its role and evolve to turn virtue into vice by applying best practice environmental safeguards across the entire energy value chain. Too many parts of the supposedly clean renewable industry unfortunately rely on raw materials that are exploited in ways that are anything but good for the environment. But by leveraging the environmental knowledge and the in-house geoscience expertise, oil and gas companies can transform and add value by encompassing all aspects of the energy resources chain rather than focusing on downstream aspects of renewable energy where their competitive advantage may be less. Lindsay touched on this earlier, but this slide illustrates how the configuration of a vertically integrated oil and gas company might change to address the energy transition while keeping the best of its competitive advantage and redeploying its intrinsic strengths. Many of the aspects are common across the two models, but energy minerals exploration and enhanced geothermal become part of the portfolio as companies change to control all aspects of the energy value chain. This slide looks at some of the workforce and technology strategies companies might consider as they adapt to the changing world energy environment. Oil and gas and minerals companies typically benefit from a highly trained professional workforce of geoscientists and engineers, sometimes with centuries of accumulated knowledge, and this drives the core business. But these people are often the first to be laid off in times of uncertainty, which really isn't all that rational. So what if, instead of laying off staff and heading off on forays into unfamiliar business streams, companies analyse their competitive strengths and harness the corporate knowledge and expertise of their professional staff to expand into more focused lines of effort and build integrated energy enterprises by becoming involved across the entire energy resources value chain, as illustrated in the previous slide. So what could that look like? Perhaps a workforce where everyone contributes with certified skill sets across disciplines and flexibly assigned according to well-mapped competencies across a range of projects, and working in mission-oriented task groups supported by some form of retained talent pool or expert advisory panel, all backed up by fit-for-purpose R&D. Leadership would be appointed on a project basis for their capability or skills rather than as a hierarchical function. On the next slide, I'll look at some of the competency mapping that we've been doing, and hopefully this will help to illustrate the point. This expands on the competency mapping I referred to in the previous slide. It's an example of how competencies for play analysis across hydrocarbons and minerals compare. There's a very high degree of similarity which is repeated in comparisons for other geoscience functions. This supports the contentions that a hydrocarbons-focused workforce can realistically be redeployed to address a wider energy minerals exploration and development requirement in the future. I'll hand back now to Lindsay for some considerations on critical minerals.
Yeah, thanks, Dave. I have 5 slides to briefly convey some exploration concepts before Dave finishes the presentation with some final observations and conclusions in slides 20 and 21. Lithium brine production is herein speculated from fossil salt basins. In this context, the massive halite of the Amadeus and the Officer basins of Central Australia. Other basins shown in Australia in grey, 2 have demonstrated alkali and metal potential, particularly the Adavale in Queensland, but the Amadeus and Officer are interesting because of the sheer scale of the salt accumulations, and more interestingly because the conventional wisdom would see a massive halite system not very prospective for lithium. The concept is based on a source reservoir pairing of an Archean and Proterozoic basement lithium source and a Neo-Proterozoic dolomite evaporite reservoir sequence for alkali metals, including lithium. The central figure in this slide is a paleogeographic cartoon representation of the Centralian superbasin as an intracratonic sag in the Neo-Proterozoic, bounded by the Pilbara, Yilgarn and Gawler cratons, and an ephemeral seaway is depicted to the northeast, with increasingly restrictive conditions toward the southwest at the time of the deposition of the Neoproterozoic evaporite dolomite sequences. These sequences are highlighted in the yellow rectangle on the stratigraphic chart. In the lower right corner of the slide is a figure from a thesis by Robert Clabe, which shows carbon isotope excursions that are likely based on evaporitic lacustrine conditions, which one can imagine presents the opportunity for a paleo environment in the Cryogenian, where ocean waters from the south and west could leach through the Archean and Proterozoic cratons and into the intracratonic sag. The Amadeus and Officer basins, in this case, were isolated from the marine incursions in the north of the Centralian Basin, leading to the deposition of alkali metals in lacustrine evaporites. The stratigraphic column shows significant unconformities above the evaporites, and these are related to the orogenic movements that reconfigured the Centralian superbasin in the south, at least, into the Officer and Amadeus basins. In this slide, we're representing lithium system event charts for stratiform play and halokinetic play, and the seismic shows salt extent as yellow fill. In the center of the slide, we have a traffic light map that we consider for the two lithium plays for the Amadeus Basin. It's all very speculative, but the point is to demonstrate an application of play-based exploration techniques beyond petroleum and the tools that geologists can apply in different ways to critical minerals, in this case, and certainly at a new ventures level. I'm including this slide on helium because it is such an obvious candidate for play-based exploration that I wouldn't want to appear to have missed it, but I won't be spending any time on it. It's just here for record for the presentation. I'm including this slide for Paleoproterozoic and Mesoproterozoic flake graphite to suggest that integrating hard rock and soft rock structural analysis and paleogeographic reconstructions would be a useful way to attempt prediction for as yet undiscovered play fairways for graphite resources, particularly when outcrop is under sufficient cover sequence. To do this, in addition to using existing magnetics, gravity, radiometrics, and electrical methods for direct detection of graphite, one could predict new play fairways and test them, at least initially, using relatively inexpensive but targeted reconnaissance geophysics. So it's not always about PBE, sometimes it's about exploration technique as well. In any case, with that, I'm handing over to Dave for final observations and conclusions.
Thanks, Lindsay. Before concluding, I'd just like to touch on some of the reasons oil and gas companies need to evolve. Firstly, in a more activist-influenced investor market, companies need to ensure that all aspects of the energy resources chain that drives their business are under their control, or that they can demonstrably operate to equivalent standards. I mean, there may well be a case for development of international criteria and benchmarks for certifiable standards in sustainable exploration, something that could help get the message across, and something better driven by industry than activists. This will impose a cost though, but a pricing premium can be justified on environmental and sustainability grounds, much in the same way that people will pay extra for locally sourced organic products. Further pricing support could be derived from the geostrategic interest of governments to ensure access to critical resources, and that could sustain less economic exploration settings to guarantee security of supply. These factors could combine to support the concept of a future integrated energy resources company deploying its strengths and technical workforce to generate competitive advantage and value. To conclude, there's an important place for hydrocarbons in the global energy mix over the next few decades at the very least, and there's a continuing role for oil and gas companies. But they need to chart their course into the future with care. Diversification or substitution of business into areas where they have little competitive advantage and have to rely on unsustainable resource exploration practices carried out by third parties for components of the energy value chain may be less successful than playing to their strengths and expanding E&P activities to encompass the whole energy value chain themselves. And this model could be equally achievable for minerals companies expanding into energy resources. So thank you on behalf of Lindsay and myself. If you'd like any further information or any clarification, please get in touch. Thanks.
I'll now introduce our final speaker in Jesse Edmondson with Graphite, the other energy carbon. Jesse's affiliation is with US Critical Minerals. In this presentation, Jesse reviews for graphite issues including the global supply chain, an overview of graphite exploration, and the challenges and opportunities for graphite supply in the United States. Jesse has a bachelor's degree in geology and a master's in science from the University of Arkansas. Jesse is focused on helping establish sustainable domestic supply chains of raw materials for energy storage, aerospace, defence, and necessary 21st century technologies. Jesse is chair of the EMD's Critical Minerals Committee. Welcome, Jesse.
Hi, my name is Jesse Edmondson. I'm the chair of the Critical Minerals Committee for AAPG-Energy Mineral Division, and I'm also the CEO of US Critical Minerals. Today I'm going to talk to you guys about graphite, which is, I'm going to argue, one of the most important forms of carbon for the 21st century. Okay, so graphite is a critical mineral, so let's talk about what that means very quickly. So here's an abbreviated definition for the United States Geological Survey, which says that critical minerals are non-fuel minerals essential to the economic and national security of the United States. They're particularly vulnerable to supply chain disruptions, and they serve an essential function in the manufacturing of a product that we cannot live without. And so different governments and agencies maintain their own critical minerals list based on what is important to them and how they are vulnerable. These lists are meant to be dynamic and change over time as technology, economies, and supply chains evolve. The graph on the right has the critical minerals list and illustrates our severe vulnerability and reliance mainly to China. Note that for 15 of these minerals, we are essentially 100% dependent on imports of these materials, and this includes graphite. As you look at the list, I also want to point out that these are mainly actual elements that are determined to be critical. I'm pointing this out because what is actually critical is that we have access to the materials that are technology ready. This is what is in demand and where our current supply chains are most vulnerable. Modern technology utilizes the very unique properties of elements or specialized compounds to work. And so we're really talking about high purity specialty chemicals and advanced materials. So there are two parts to solving these supply chain issues. Number one is the mining aspect. So we have to excavate the rock and process the material into a mineral concentrate, which is all typically done at the mine site. And then there's the advanced material manufacturing, which this is how we convert these materials from run-of-mine mineral concentrates into usable technology-ready materials. So in order for most new critical mineral projects in the United States to be economically competitive, they have to be vertically integrated, meaning that they have to do both the mining and the advanced processing. This illustration is from the Benchmark Mineral Intelligence Team, which is the leading authority on the complexities of the lithium-ion battery supply chain. This graph illustrates the flow of battery materials from the mine all the way downstream to the battery manufacturers, and clearly highlights that China currently dominates almost the entire lithium-ion battery supply chain, particularly compared to the United States and Europe. If we just focus on the mining stage in the top left and the chemical processing stage in the top right, we can see that China controls 65% of the global supply of run-of-mine flake graphite. However, they're able to control approximately 100% of the global supply of battery-ready graphite by controlling the downstream conversion capacity, 100%. So having the mines is helpful, but in order for 100% security of supply, it's necessary to also have the advanced manufacturing capability to convert the raw mine material to a technology-ready product. All right, so now let's talk a little bit about what is graphite. So graphite is crystalline carbon. Okay, so it occurs both naturally and also artificially. It's a very useful material. It has a high resistance to heat. It's electrically conductive. It also makes a great lubricant. So it's actually found in over 600 applications, but the demand is driven by lithium-ion batteries, where it is currently the main component of the anode in this battery technology. Graphite is also used as a conductivity enhancement material where it can be used in just about every battery chemistry. So ranging from lead acid, traditional alkaline, but to also kind of next generation lithium, sulfur, and zinc air battery technology. According to the World Bank, with a recent report that came out earlier this year, demand for graphite will increase by over 500% by the year 2050, again, driven largely by its use in battery technology. According to Benchmark Mineral Intelligence, in 2019, the graphite anode market was approximately 56% synthetic versus 41% natural. So that equates to 111,000 tons of synthetic graphite versus 64,000 tons of natural graphite. Keep in mind, this is just for the graphite anode market in lithium-ion batteries. Okay, so looking at natural graphite, it naturally occurs in several forms: vein graphite, amorphous, and flake. Flake graphite is the most useful form. It can be transformed into a wide range of technologies, so that's typically what's focused on as far as bringing on new sources worldwide. If you look at flake graphite, over 65% of global production of run-of-mine flake graphite is controlled by China. And as discussed earlier, they control almost 100% of the battery-ready graphite. The pros and cons of natural graphite versus synthetic. The pros are it's a cheaper material, it has a higher energy capacity, and it's a very soft and malleable material, which allows it to be better for shaping and for exfoliation. The cons of natural graphite are the quality and consistency issues that can vary, even from using material from the same mine. So just minor differences in the chemical composition of the rock can lead to variations in the quality of the final battery quality graphite, and this can have detrimental effects to electrochemical performance. Natural graphite also has a weaker cycle life on average compared to synthetic graphite, and this is particularly important for using graphite in EV applications. All right, now looking at synthetic graphite really quick. Synthetic graphite is manufactured from petroleum or coal-based coke. Over 85% of synthetic graphite that's utilized today in batteries is also produced in China. And it's important to note that not only does China currently dominate, but they have aggressive plans to expand their production capacity. Again, comparing synthetic graphite to natural graphite, the pros of synthetic graphite is historically you've been able to control more of the quality and the consistency of the material compared to naturally sourced graphite. Synthetic graphite on average has better cycle life performance that again is very important for electric vehicles. And advanced forms of graphitization with kind of new novelty materials allows for better custom tailoring. However, the cons for synthetic graphite is the high quality precursor material can be subject to supply chain shortages and drastic price fluctuations. This is particularly true for needle coke, which is the preferred precursor material for anode graphite in electric vehicles. Synthetic graphite also has a much higher CO2 footprint. The process of turning petroleum coke into a precursor material and then also converting that material into a battery material involves a very energy intensive thermal process. So it can have a massive CO2 footprint, not to mention the CO2 footprint associated with the production of the petroleum and coal in the first place. But for the combination of these reasons, synthetic graphite is more expensive to customers than natural graphite. I just want to kind of review this quickly, but the point that I'm trying to make here is that the synthetic graphite supply chain is extremely complicated. And so if you look at kind of the first top half of the slide, this just shows the process of getting a needle coke out of either a coal or an oil. So it involves a distillation process and then also a calcining process, which is a thermally intensive process. So this is all required just to produce the needle coke, which is then used as the precursor material for graphitization. So then as you look at the bottom of the page, starting just right as synthetic graphite, this process starts after the process above is completed. Okay, so again, just trying to highlight the fact that it is a multitude of steps to get an oil-based coke into a battery quality synthetic graphite. And so again, complex supply chains, an expensive and energy intensive process. And now let's talk about how to get natural graphite out of the ground and into the anode of a lithium-ion battery, which requires graphite in the form of an ultra-high purity coated spherical graphite, a specialized advanced material. So the typical process would be to mine the rock, in this case a graphitic schist containing approximately 4% graphite or carbon. So the rock is excavated, crushed, and the graphite is then separated through a series of flotation and polishing grinding stages, which results in producing a graphite concentrate that is now approximately 95% carbon. At this stage, the material could be sold into the traditional industrial markets after the flakes are sorted by size for something in the range of $500 to $1,000 a ton. Even though the U.S. has not mined graphite since the end of World War II, run-of-mine flake graphite is not really in critical supply. It is currently abundant globally. However, specialized ultra-high purity forms of graphite are in demand, and there's a need for new reliable and secure supplies of high-quality material. So this run-of-mine graphite concentrate can then be upgraded by purification. This is typically done by either an acid or heat treatment, where the purity of the graphite is enhanced to over at least 99.95% to go into a lithium-ion battery. And then this purified graphite gets micronized, sized, shaped, and gets a specialty coating in order to make it ready for the anode of a lithium-ion battery. Note there is an order of magnitude difference in the selling price of this material by upgrading it from run-of-mine to battery quality. Okay, so what are the steps for developing a new supply of battery quality flake graphite? The map on the left illustrates areas of increased exploration activity for graphite in the last 5 to 10 years to help diversify the current supply chains outside of China. Graphite is found in metamorphic terrains where there's sufficient heat and pressure to crystallize the carbon. From an exploration standpoint, geophysics is a tool that's often used, particularly airborne EM. Graphite is a conductor, so it'll really light up at kind of the regional scale. And then when kind of those targets have been identified, you look at them closer through a series of surface mapping, trenching, and drilling to kind of define the resource. So one thing I want to point out here is that, if you look at kind of the first two items, finding the graphite, figuring out how much is there, what's the quality of the material, that would be typical for defining, kind of an ore deposit of, say, silver or gold. And at this point, if 1 and 2 are successful, you can essentially fund the mine into operation, or it becomes at least a kind of a bankable asset. But for a lot of the battery materials and critical minerals, especially graphite, it lacks a spot market. And that means that the price of the graphite is based only on having a supply contract with an end user. And that end user requires a very specific technical specification to meet their requirements to be a new material for their technology. And therefore, getting some money together for exploration and to really build out these resources is one thing. But in order to actually build out a mine and to fully commercialize an operation, it's really an intricate set of steps that requires having those final contracts in place with the customers. So it kind of leads to a chicken or the egg situation where an investor isn't going to write you the check to get into commercial production until you have those sales contracts in place with the battery end user. And then the flip side of that is you're not really going to get those contracts in place with the customers until they've been able to fully test and qualify your material. Okay, and so proving that you've got graphite in the ground is an important step, but it's really only part of the process. Okay, what's equally as important is proving that you can make a battery grade product by doing your own kind of internal testing and development, then sharing that material with customers to where they give you feedback that you've in fact made a good material. But in order to really get your material qualified into a lithium-ion battery, this can be a 2 to 3 year process. And it really requires that you have the on-site demonstration plant where you're making the material for your customers with your equipment, your rock, and everything. And so it's really hard to get, from step 1, 2, 3, and 4 to 5 and 6. 5 and 6 have really been the deal breakers for all these projects because even building that demonstration scale capacity, that can be something that requires tens of millions of dollars in investment. And again, that doesn't necessarily guarantee the project's success. It just gets your foot in the door with those customers to kind of build out those agreements. So, building out a new graphite supply chain takes time. It takes money. The process of from exploration to commercializing a mine is going to be at least a 10-year process in just about every case. And on top of that, you're looking at, $3 to $5 million for exploration, another $3 to $5 million for kind of proving feasibility, building those qualification plants, or the on-site demonstration plants. That can be something that costs $10 to even $20 million. And then full-scale commercialization, if you're doing both mining and the advanced processing, you're looking at a cost on the north of $100 million and can even be several hundreds of millions of dollars. So here's just some suggested web resources for kind of continued reading on critical minerals in general. Happy to share that with the group. And with that, that's the end of the presentation. As my contact information, please reach out if you have any additional questions. Thank you.